Hello everyone, welcome. This is paper 2 from May 2025 and this is time zone 3. Let's have a look and see what we can do. Here we go. Question 1. Kathy is a financial analyst studying the growth of two investment accounts, account 1 and account 2 for a new client. Account 1 has an initial amount of $5,000. Interest is added to the amount in account 1 at the end of each year in the following manner. $200 at the end of the first year, $260 at the end of the second year, $320 at the end of the third year, $380 at the end of the fourth year, $440 at the end of the fifth year. Assume the amount of interest continues to increase each year so that it follows, and this is key, an arithmetic sequence. So, question A. Part 1 asks us to find the common difference. So common difference for an arithmetic sequence is the value that we need to add or subtract to go from one term to the next. So here we see term 1, term 2, term 3, term 4, and so on. And the question is, what value are we adding or subtracting to go from one term to the next? So I think you can probably see this already, but I'll write these out. 260, 320, 380. And the question is, what are we adding to go from one term to the next? Well, in this case, we're adding 60 every single time. If it was more challenging, or if it was like more involved of a question, we can always just find the difference by u2 minus u1, or any term subtracted from the previous. So 260 minus 200, what's the difference? Well, 60. And that's going to be the difference that we add to go from one term to the next. So in this case, D, the common difference is equal to 60. All right. Part 2. Find the amount of interest in USD added at the end of the 10th year. So we have this arithmetic sequence already. I suppose we could just look at first, second, third, fourth, fifth, and then just keep adding 60 until we get to the 10th. And that would certainly work. But I think it might be, a little more concrete and maybe give us a little more assurance, I suppose, if we write out the general term of an arithmetic sequence. So what is the formula that allows us to find any term within a sequence? This is given to us in our formula booklet. It's un, value of a term, is equal to u1, value of the first term, plus n minus 1, n being the term that we substitute, and d is a common difference. So in this case, we know u1, the value of the first term, that's how much interest we add in the first year, plus n, remember, is just the term number that we substitute. It's the term value that we want to solve for in any given situation. And d, the common difference we found, was equal to 60. So that's our formula for our general term of an arithmetic sequence. All right. So now let's find u10. So in this case, we want to find the interest in the 10th year. That would be when n itself is equal to 10. So essentially, we want to find the value of term 10. So wherever we see an n, let's replace it with 10. And then we'll write 2,000 plus, in this case, 10 minus 1 times 60. What is the value of u10? 200 plus, this is going to be 9 times 60. So just writing this out, we have 200 plus 9 times 60. 9 times 6 is 54, so 9 times 60 is 540. 540 plus 200 will give us 740. So in this case, the answer would be 740, in this case, USD. So they're adding 740 USD. Maybe I'll write a dollar symbol here. All right. So that would be the amount of interest earned or added to the account in the 10th year. All right. Moving on. Part B, show that the amount of money in account 1 after n years may be expressed as 5,000 plus n over 2, open bracket, 340 plus 60n. So 5,000 plus n over 2 multiplied by 340 plus 60n. All right, so amount of money that we'll have in the account will be it'll be the total amount of money, that initial 5,000 that we invested initially, and then the amount of interest that we earn through time. In this case, we just want to talk about n years, not the first, second, third, fourth, but generally. So n years, however many years we're talking about. So in this case, we want to find, once again, initial amount of money plus total interest added. Since we're talking about a total interest added, we want to find the sum of all the interest. So in this case, we'll use our sum formula. We have two sum formulas in the formula booklet. We have Sn is equal to n over 2, u1 plus un. And we also have Sn is equal to n over 2. Then we have 2u1 plus n minus 1 d. And these are equivalent formulas. They're just expressed in different forms. The only thing that is different between these two is instead of un, this value of the final term, we replace this un with u1 plus n minus 1d. And by doing that, replacing this un with u1 plus n minus 1d, we're now going to have two u1s, and we're going to have this n minus 1d. So this is helpful if we don't actually know the value of that final term. Sometimes we will, but in this case, we actually don't know necessarily what the value of that final term is going to be, because we actually don't even know how many terms we're, let's say, even concerned with. So we want to generalize. We don't know the value of that final term, so let's use this formula for the sum. All right. So let's go ahead and find the sum of interest over n years. So Sn is equal to n over 2, 2 times u1. u1 was how much interest was added in the first year, and that's 200 USD, plus n minus 1, and then the common difference was equal to 60. Okay, so now we can clean this up a little. So we'll have n over 2, 2 times 200, just working with this here, is going to give us 400 plus, and now we're going to need to use, I'm not sure what you may call this, but the rainbow method or distribution, where we're going to multiply this coefficient, or this number on the outside, by all the terms on the inside. So 60 times n is going to give us, 60 times n, is going to give us 60n. And 60 times negative 1 is just going to give us negative 60. So just to reiterate, I think I mentioned this in another video, but if you have something like this, 60 times n minus 1 or n minus 1 times 60, they're the same thing. Sometimes, or most often, we distribute with the number out in front, but it means the exact same thing. When we multiply, the order doesn't matter. A times b is equal to b times a. So let's keep going here. I think we can clean this part up, and then I think we'll get this form generally. So n over 2 and now we have grouping like terms. 400 minus 60 is going to give us 340, and then we have 60n just sitting by itself, I suppose. Okay. So this is the total amount of interest that is paid out over n years. So total amount of interest over 1, 2, 3, 4, 5, or however many years we want. But the person who is vesting, or that wants to open this account, they make an initial deposit of $5,000. So in terms of the total money that they'll have in their account, it's not just going to be the interest. It's going to be, well, added to the initial amount that they also deposited. So if we want to talk about the total itself will be, what can we say? The initial deposit plus the interest earned. I guess we could say the total interest earned. The initial deposit was itself $5,000, and the interest earned is n over 2, and this is 340 plus 60n, which is exactly what we see here. Okay, so once again, initial deposit plus interest earned. Interest earned is summed or added together through time. That would be our sum formula. A little bit of algebra here, but then we work it out to get the same form. Okay, moving on, part C. Hence or otherwise, find the amount of money in account 1 at the end of 10 years. So hence or otherwise means we have some choice. Hence itself means draw on what has previously come before. And I think it actually will be easier if we draw on the formula that we found. So how much money does someone have in the account after 10 years? Essentially, we're asking to find Sn when n is equal to 10, or essentially, we're asking to find S10. We actually have this formula right here. This is Sn right here. So let's take this and let's bring it to the other page, and we'll use this to solve for C. Actually, let's write it here. I think that should be fine. Let me just maybe put a line between these, just so we can say that we are doing something new. Okay. Okay. All right. So in this case, we want to find S10, the sum or the total amount of money that they have after 10 years. So S10, wherever we see an n, let's replace it with a 10. So 5,000 initial deposit plus 10 over 2 multiplied by 340 plus 60, and then n once again is 10. Okay, so it looks like we've got everything we need here. Let's go into the calculator and solve. So here we are. 5,000 plus 10 over 2 is equal to 5, but you can write it out as a fraction. 340 plus 60, plus 60 times 10. All right, I think that looks good. And we have $9,700. That will be the total amount of money in the account after 10 years. So let's go back to the document and write that out. S10 is equal to 9,700. Let's make a little room and put the dollar sign. All right, so looks good so far. Let's go on. Here we've got account 2 now. Account 2 has the same initial amount of 5,000 USD. Account 2 pays 6.5% interest compounded annually. The interest is added to the amount in the account at the end of each year. The amount in account 2 after n years can be expressed as 5,000 times b to the n, where b itself is an element of the real numbers. So that essentially means that b could be positive, negative, a fraction, doesn't need to be a whole number. So b is positive, negative, and then it doesn't need to be a whole number. It could be a fraction, a decimal, so on and so on. All right, so part 1 of part D, write down the value of b. All right, so this is essentially an exponential equation or an exponential function. This is our initial starting amount, which matches this 5,000 USD. And this is, when we're talking about a geometric sequence, this is our growth rate. This is the value that we multiply by to go from one term to the next, or our common ratio. For a compounded interest, this would be not entirely our interest rate, but the value which our account increases by every year. That is to say, if we take some initial value, what do we multiply it by to go from one term to the next? So 2 different ways we can work this out. I think we can work this out conceptually, or we can work it out using compound interest. I think compound interest might be the most straightforward. So let's go with that. So we're told the amount of money in the account is compounded annually, and it pays out 6.5% interest. So our compound interest formula, we can actually go to this in the formula booklet. I believe this is under, I think it's under number and algebra actually. Here it is. Compound interest. Compound interest is PV, present value, 1 plus R, our interest rate. K is the number of compounding periods per year, so it's like monthly or weekly or biannually. And N is total number of years. So let's actually use this compound interest formula and then we'll see. I think the question is essentially, what is all of this business, within these brackets here? What is this thing that we are raising to the power of n? And that's going to be what b is in this situation. That's going to be this thing right here. What is it that we're raising to the power of n? So let's write out the compound interest formula, fill it in, and then we'll try to match b. So here we go. Final value of an investment is equal to present value multiplied by 1 plus r over 100 times k raised to the power of n times k. Present value is $5,000. That's that initial amount that they put in, and that matches this. 1 plus r is our interest rate, which is 6.5 over 100. Number of compounding periods per year, it's just compounded annually, so it's actually just 100 times 1, or just 100. We don't need to write 100 times 1. And actually, in this case, I don't think I'm going to, just because I think it's going to clutter things up too much. So, and then we have n times k. N, in this case, we want to generalize, so we're not saying 5 years, 10 years. Let's just leave it as n. And then once again, it's going to be n times 1, which is just going to be n. All right. So now we've got a form that's very, very similar to this. We've got this 5,000 here, 5,000 here, and then we have something being raised to the power of n. So let's go and simplify everything within these brackets. So 5,000 times 1 plus 6.5 over 100. You can put this into the calculator if you want, but it's 0.065. 0.065. Essentially, it's a percent represented as a decimal. 6.5% is equal to 0.065 as a decimal. And this is raised to the power of n. And lastly, 5,000. 1 plus 0.065 is just going to be 1.065 raised to the power of n. And if we compare this right down here with what we have right here, we can see that b itself must be equal to 1.065. So write down the value of b. B itself is equal to 1.065. Okay, I think that's certainly one way to do it, and maybe the most familiar in some ways. Another way that I think you could potentially do this is, I think for arithmetic and geometric sequences, writing out a table is always nice. So if we have, in this case, n, the term number, or in this case, the number of years, and then we have, what can we say? I guess we can say the value, or yeah, let's use v for the value in our account. When we just deposit the account, we have, well, this would be term 0, no amount of time has passed, but we have 5,000 in our account. After 1 year, we know we have 5% more than we had originally, because we get 6.5% interest. So in this case, since we're dealing with a geometric sequence, since we gain 6.5% interest, how much would we have at the end of our first year putting this money into an account? Well, we would multiply by what? We can't just multiply by 0.65, because that would mean our money would, in some sense, evaporate. We would only have 6.5% of what we had. So in this case, we have the money that we had initially, that 100%, plus we have 6.5% more, or essentially we have 106.5%. As a decimal, remember as a decimal, convert percent to decimal, move over to right, move the decimal place 2 to the left, or divide by 100, and in the end we'll have 1.065. So in this case, 5,000 times 1.065, we have 6.5% more than we did in our original, starting value. And in this case, that would be the amount that we would have in the first year. This is our common ratio, what we multiply by to go from one term to the next. And remember, for our arithmetic, not our arithmetic, our geometric sequence, we have u1 times r n minus 1. And then once again, comparing that to this, u1, value of the first term, times r. R is the common ratio, what we multiply by to go from one term to the next, raised to the power of, in this case it's n, where we have n minus 1, that's just because we're starting at the 0th term, and it's maybe slightly different. But this is still our common ratio, what we multiply by to go from one term to the next. Okay, another way to solve it and find this value of 1.065. Okay. Part 2, hence or otherwise, show that account 1 will have more money than account 2 at the end of 10 years. Okay. So we already know how much account 1 has at the end of 10 years. Let's find out how much account 2 has at the end of 10 years using this value right here, this expression. So initial value times b, which we found, raised to the power of n. This will give us the total amount, or, just like we worked out here, the final value. So let's actually go ahead and use this. I'm gonna maybe copy this, and we can go ahead and put in some value in for n, in this case 10, and we'll see how much money they have at the end of 10 years. So final value after 10 years, in this case n itself would be equal to 10. So 1.065, in this case we want to solve when n is equal to 10. So let's raise this to the power of 10. Let's go to the calculator here and work this out. 5,000 times, actually let's open up a bracket, 1.065 raised to the power of 10. All right, so they have $9,385.69. So they have less than they would have if they had chosen count 1. Let's go back to the document and write this out. So we have $9,385.69. So I'm going to grab this and bring this up. Hence or otherwise, show that account 1 will have more money than account 2 at the end of 10 years. So how can we show that? Because we know, for example, that, actually I don't need to copy that. We know that $9,700, that's how much we have in account 1, is greater than $9,385.69. All right. Let's keep going. The client is interested in a longer-term investment. Kathy finds that it will take at least m complete years for the amount in account 2 to exceed the amount in account 1. Part E asks us to find the value of m, and it's a 3-mark question. Okay, so there's going to be some point in time where account 2 is going to have more money in it than account 1. We already have 2 equations that tell us the amount of money in an account, and it's linked to a value of n, or time. So what this means is we can put in some value of n into this equation, and it will tell us the amount of money that we have at the given time, after 1, 2, 3, 4, 5 years. And this is for the compound interest question. And this is where our interest is increasing arithmetically, in terms of an arithmetic sequence. This is the equation, or the function, which tells us the amount of money we'll have in an account for any given year, for any value of n. So what we can do is we can compare these two. So I'm going to clear this up, and then let's write out some comparison linking these two functions. Okay. So this is all we really need here, and I think we're good. So I want to keep this. This represents the amount of money we have in account 2. But what about account 1? Actually, let's go up and just grab this. Okay. Here is account 1. All right. So this is an equation which links the amount to some given value of n and amount to some given value of n. What we want to ask is, when is account 2 greater than account 1? So this is account 2 right here. Let's substitute that value. Essentially, we're asking, when is this 5,000? 1.065 raised to the power of n. When is this value greater than account 1? And this is the equation which represents account 1. 5,000 plus n over 2, 340 plus 60n. Okay, so we know that, or I guess we can assume in some ways, that finding after 10 years, account 1 was greater than account 2. But since account 2 is an exponential, that means it grows like this, eventually this will catch up to account 1. So a strategy, I think, one possible strategy, is to, in some ways, set these equal to each other, find the value of n that makes this true. In what year are they going to be equal to each other? And then if we know this account 2 is an exponential that is catching up, constantly catching up to a1, then if we find the point where they're going to be equal, then we know the year after that will be, well, the point in which they are, or sorry, that a2 will be greater. So find when they're equal. a2 as an exponential is catching up. The point in which they're equal is, well, when they have the same amount. And since this one's growing quicker, right after that, it will be greater. I think that's a strategy that we can use. So let's go ahead and n solve this. We'll find out the point of n where they're equal to each other, and then we'll see what we can do with that. Okay, so here we are in the calculator. Let's set up an equation. So here is a2, 1.065 raised to the power of n. And this is 5,000 plus, and then it was n over 2, and here it was 340 plus 60n. All right, and then we want the calculator to solve for n. So here we go. This is equation 1. When does equation 2 equal equation 2? And this is 0. Actually, this is okay, because essentially what they're saying is, or what nsolve is saying, is this is the point in which they are, or there we are. They're saying, when we put this in, a2 is equal to a1. When does this occur? nsolve is saying, well, at year 0. And that's technically true. When 0 years have elapsed, they both have $5,000 in the account. So that's going to be one value, or one solution of n, that balances this equation. And that's actually how nsolve works. nsolve starts at 0, and then it goes left, right, left, right, left, right, to find the points of intersection that are closest to 0. In this case, 0 is a solution, so it's reasonable. So let's start off at 1. Let's ask nsolve to choose the lower bound of 1 and find anything greater than this. And here, rather strangely enough, we actually have 7.96, which suggests that at 7.96, they have the same value in the account, which is a little peculiar because after 10 years, we found out that account 1 actually had more. So this is a little confusing. What I want to do is actually I want to find if there's any greater value than this, because this I think will tell us essentially, well, maybe what's going on as well. So let's start at 8 and ask nsolve to go forward. So 38. So 38 is another solution. And I'm guessing, actually I kind of know in a sense, that there's going to be nothing beyond 39. I think it's going to say no solution found. Okay. So what's interesting here is we actually have 3 points of intersection. 0, where at 0 years they both have 5,000. That makes sense. And then it also tells us at roughly 7.9 years they're going to have the same amount. And after 38 years, they're going to have the same amount, which is kind of peculiar. So maybe let's go into our graphing calculator and see what's going on here. So let's graph these functions, and I think this will give us a better idea. So 5,000 times 1.065, then we'll raise this to the power of n, but since this is in terms of x, we have to write x. Okay, I'm going to zoom fit. Hopefully this works. That's not too bad. Menu, we'll get another graph, and this time we'll put that function that was growing with this interest rate that proceeds arithmetically. 5,000 plus, and then once again x over 2, and then 340 plus 60, and then x, because we can't use n. All right, so I'm going to zoom out. Again, they start at the same value. They both start at 5,000. Remember, this is function 2. So what's kind of strange is that function 2 is actually greater than function 1 up until around 7.9 years. And then function 1, or account 1, this arithmetic increase of interest, becomes larger. But let's zoom out a little. This is somewhat interesting here. And then, here we go. And then there's another point in which account 2 overtakes. So this will link to those amounts that we found with nsolve. So I'm going to analyze graph and find the intersections. This is going to be that 7.96 that we found. Analyze graph, intersection, and this is 38.04. So to be honest, I'm not a great fan of this question because in the original question it says, Kathy finds that it will take at least m complete years for the amount in account 2 to exceed the amount in account 1. Well, technically speaking, after 1 year, the amount in account 2 is greater than the amount of account 1. And this is actually true for the first, 7 years. For the first 7 years, account 2, this blue line right here, is above the red line. So for the first 7 years, actually, account 2 exceeds account 1. Of course, from 8 years all the way to 38, that's not the case. Only after 38 years does account 2 then take over. But that's, to be honest, in a real-life context, this is a heck of a long time to potentially have money in account. Not impossible, but I would say in terms of, I guess, the structuring of this question, Kathy finds that it will take at least m complete years for the amount in account 2 to exceed the amount in account 1. Well, technically at year 1 or year 2, it's exceeding. But long term, when does it exceed account 1 and then kind of never look back? Well, after 38 years. So the value of m that I believe they're looking for here is 38. Actually, I didn't know it is. This is the one that they're looking for, 38 years, 38.046. Okay, so let's go back to the document and we'll write this out. So here we are. So when n is equal to 38.046, and let's actually look at this. So it says m is complete years. So what this means in practice, this n right here of 38.046, it means that slightly after the 38th year, they're equal. But since the interest is paid out at the end of a year, or in this case, yeah, both of them actually have the interest being paid at the end of the year, it's not going to be slightly into year 38 where they're equal. It's not going to be until the 39th year. So 38.046, they're equal to each other. Interest is paid out at the end of the year. So in terms of the number of complete years, it's not until the 39th year. So n is equal to 39, and in this case, m itself, the number of years it will take for account 2 to overtake 1 is 39 years. Okay, so I think a challenging question just because it's a quadratic and an exponential, and there are actually 3 points of intersection, which makes it a little unusual. And to be honest, maybe this is unfair kind of criticism, but I think there's actually some ambiguity in this question, because technically at year 1, account 2 exceeds the amount of account 1. Potentially. I think there's some ambiguity. Okay, let's go on to part F. Determine the total interest added to account 2 at the end of m years Give your answer correct to the nearest dollar. Okay. So here's account 2. Here is our equation that tells us the amount we'll have at any given time. All we need to do is substitute some value in for n. So after 39 years, how much money do we have in account 2? I think that's going to be our strategy to solve this. So let's look at account 2 and let's see how much money they have in the account when n is equal to 39. So after 39 years. So final value after 39 years is equal to 5,000 multiplied by 1.065 raised to the power of 39. So this is after 39 years. So let's go to the calculator and work this out. So 5,000 times 1.065 raised to the power of 39. I think we're going to need a few more digits potentially. So I'm going to increase the float to 8. And I'm going to work this out. All right, so $58,291.43. So let's go back to the document and work this out. Final value, $58,291.43. But they're not asking for the total amount, they're just asking for the interest that was added at the end of M, or in this case, 39 years. So the total amount is itself made up of, well, our initial deposit, how much money we put in at the very beginning, plus the interest that we've earned. In this case, we know the total deposit, the total amount that we have is around $58,291. But not all of this is interest because we made a $5,000 initial deposit. So what is left over after we remove this $5,000 initial deposit? All of what remains is going to be interest. So we put in 5,000 initially. It's grown to 58. So everything above that initial 5,000 is interest. So let's find our interest. Essentially, we're going to rearrange this. And we will have interest is equal to the final amount minus initial deposit of 5,000. And this in the end is going to be $291.43. So sorry, not 5,000, $53,291.43. To the nearest dollar, this is going to be $53,291. All right. Good. Moving on to question 2. A company produces electronic components on a large scale. They carry out quality control tests to determine whether the components meet the company's standards. Sakir, the owner of the company, wants the quality control team to analyze the distribution of the weights of the components. Keyword is distribution. Based on historical data, the quality control team knows that the weights of the components follow a normal distribution with a mean of 2.5 grams and standard deviation of 0.15 grams. Part A. Find the probability that the weight of a component selected at random is greater than 2.8 grams. So some key information here. We've got a normal distribution, so we're in the realm of this normal distribution, and we have a mean and standard deviation. Now we want to find the probability that some component is greater than 2.8 grams. So I'm actually going to sketch this out because I think sketches for normal distributions really help show what's going on. And they're also a way to get method marks, potentially, as well. So probability that the weight of a component is greater than 2.8 grams. So what do we have here? We have a normal distribution, symmetrical about the mean. Mean itself is 2.5 grams, and the standard deviation right here is 0.15 grams. So if we wanted to, not necessary, but we could write 0.15 grams. And we want to find the probability that a component selected at random is greater than 2.8. So what is 2.8 here? 2.8 might be something right about here, I suppose. Maybe that's 2.8. And the question is, what is the area, or what is the percentage under the curve that is greater than 2.8? So once again, normal distribution. Underneath the normal distribution is every single possible value. The area under the curve is equal to 1, just like the probability of 1 encapsulates or captures everything, 100% of our data. And so in this case, we want to find the area under the curve, or the percentage of space you can imagine that is 2.8 or greater. And that will tell us the probability that, in this case, one of these components is greater than 2.8 grams. So in this case, we've got a normal distribution, we've got a mean standard deviation. We should be able to go to the calculator and use normal distribution. So here we are. Menu, we'll go into probability, distributions, and let's go normal CDF. Lower bound is 2.8. Upper bound, we just want to make sure that we capture everything to the right. Reasonably, we could put 10 grams, but let's just put 999 just to make sure. The mean itself is 2.5 grams. Standard deviation is 0.15. All right, so the probability that we have a component that is greater than 2.8 grams is roughly equal to 0.02275, or 2.28%, I guess. So let's go back to the document and write this out. So let's see. If we wanted to write this out a little more formally, I suppose, we could write this out as the probability that weight itself is greater than 2.8. And then we could write our answer for that. The IB also accepts calculator notation as well. So we could also write, for example, norm CDF, lower bound, upper bound, and this one might be a little different. If you've chosen, let's say 100, mean standard deviation. And then our answer in the end was 0.0228. 228. If you want, you can represent that as a percentage, and that's fine as well. Moving on here, the probability that the weight of a component selected at random is greater than W grams is 0.8. Part 1 of B asks us to sketch a diagram of a normal curve to show the area represented by this probability. All right, so let's sketch a normal curve. So this is the same normal curve as originally, as the one we have here. It's centered and symmetric about the mean. Mean is 2.5. And in this case, we want the probability of a weight selected at random is greater than 0.8. So essentially, we want to choose a weight, a component, and we want, a way to rephrase this is we want 80% of our components, essentially, to be greater than some value. So if we know on average, the weight of these components are 2.5, if we want 80% of our components to be greater than some cutoff point, we know that cutoff point is going to be, well, on the lower side. So let's actually draw this cutoff point here. And this is going to be W, this cutoff point. And we know 80% of the components are going to be greater than this cutoff point W. And this is actually, it's a nice question because it's, the opposite in some sense of this first question. In the first question, they gave us this lower bound of 2.8, and they said, what is the probability? What is the percentage of units, essentially, that are greater than this lower bound? Here, for example, they're giving us the probability, or the percentage of units. They're saying 80% of the units are greater than, and now they're asking you to find the lower bound. So this was a classic kind of normal distribution question. Here's a lower bound, or here's a cutoff point essentially, what is the probability. Here they're switching things up. They're saying, here's a probability. What's the cutoff point? So in this case, here we have our classic normal, and here we have the inverse, the opposite. This is going to be our inverse normal. So let's go to the calculator and work this out. Probability, distributions, in this case we want to go inverse normal. So area, let's go back to the document for a sec. So the calculator has its conventions, and one of its conventions is it sweeps from left to right. So in terms of calculating the area, we can't just put in 0.8 because the calculator is going to sweep left to right, and it's going to find the point that captures 80% of our data. But we don't actually want that. Our calculator sweeps left to right. We want 80% to be to the right of some cutoff point, which means we're going to only want the calculator. We're only going to want the calculator to sweep through 20% of this standard normal curve to reach this value of W, because 80% is going to lie on the other side. So let's go back to the calculator here. Area, calculator sweeps left to right. Let's put 0.2, 20%, because we want 80% on the other side of this. The mean is itself 2.5. Standard deviation is 0.15. All right. So in this case, that lower bound is 2.3737, or we could say 2.37 grams. Okay, so let's go back to the document and write that out. So here it is, 2.37, and I think that's actually fine. All they want is us to sketch a diagram of the normal curve. So actually, all they wanted in this first section is a sketch to show the area represented by this probability. So if you wanted to actually write this, you probably want to take this away, and just something like this is fine. All right. Find the value of W. This is part 2. The value of W using inverse normal is 2.37. All right. So I think we're good. Maybe I'll actually just go back to the calculator just for a sec. So under inverse normal, if we had chosen an area of 0.8 and kept our standard deviation and mean is 2.5 and 0.15, we would get this value of 2.62. And going back to the calculator here, the document, if this is a value of 2.62, something like this, there's no way, for example, that 80% of our units would be greater than 2.62, because the mean itself, the dividing line, is 2.5. So 50% to the right, 50% to the left. 2.62, there's not enough space left, essentially, for 80% to be on the right side. So that would be another way to say, or to I guess remind you that calculator sweeps left to right. To pass test 1, the weight of a component must be between 2.3 grams and 2.7 grams. Find the probability that a randomly selected component passes test 1. Okay, so here we're still within the realm of normal distribution. I'm actually going to draw it once more, and just to try to give an account of what's going on, see if I can create something a little more symmetrical. All right. So once again, the mean is equal to 2.5, and in this case, we want to find the probability that a component is between 2.3 and 2.7. So in this case, let's put the lower bound of 2.3 right here, and the upper bound of 2.7 right here. Once again, everything under the curve represents the total number of components. So essentially we want to ask the question, what is the percentage between 2.3 and 2.7? What are the percentage of components between 2.3 and 2.7? What is the probability of a component being within this within this range? All right, so let's go ahead and work this out on the calculator. This is going to be normal distribution once again. Probability distributions, normal CDF. Lower bound is 2.3, upper bound is 2.7, mean is 2.1, standard deviation is 0.15. All right, so in this case, roughly 81.75% or 0.817577. Okay, so let's go back to our document and write this out. So what do we know? We know the answer in this case. So the probability that some component is greater than 2.3, less than 2.7 is equal to 0.817577, or to 3 sig figs, 0.818. As a percentage, we can also write this as 81.8%. What that means in context is if this represents all of the components that are built or that are constructed, 81.8% of them are within this range of 2.3 to 2.7 grams. All right. Question 2. Find the expected number of components in a box of 200 that will pass test 1. Okay. So we know that 81.8% of the components are between 2.3 and 2.7 grams. So if suddenly we have a box of 200 components, we know that, well, 81.8% of them are going to be between this range of 2.3 and 2.7. So what we can do is we can multiply this by, and I'm actually going to use this full accuracy or greater accuracy rather than 3 sig figs, because we're still technically within question C. So we're still within the same question. So 817577. This is the same. This is our expected frequency, and we know expected frequency is equal to the number of trials times probability of occurrence. In this case, 200 trials or 200 components. The probability that any given component is going to be within this range is 81.8%. And here we go. Let's work this out on the calculator. So 200 times 0.817577. In this case, we have 163.5. Rounding up, in this case, to 3 sig figs, we would have 164 components. So I'm going to write this out. Here we are. 163.5. Rounding up to 3 sig figs is 164. All right, moving on. Zakir asked the quality control team to conduct a more in-depth analysis by performing a new test, test 2. The probability of a component passing test 2 is 0.95. The team randomly selects one box and tests each of the 200 components. Part D asks us to find the probability that exactly 190 components pass test 2. So in this case, we have a set number of trials. We're going to test 200 components. We have probability of success. We have the number of successes, and although it doesn't state it directly, we can infer that the probability of one component passing the test is independent of the other. That is to say, if one of these 200 components fail, it doesn't make it more or less likely that the next one is going to pass or fail. So in this case, set number of trials, probability of success, probability of success stays constant, and these are independent trials. They don't influence one another. And then of course we have a set number of successes. So here we're actually in the realm of binomial distribution. And we can actually go into our calculator to work that out. So let's go And we'll go into the calculator here, menu, probability, distributions. So in this case, we're going to go into, we can use binomial PDF or CDF. In this case, we just want to find the probability that exactly 190 components pass test 2. So let's use binomial PDF here. So number of trials, we're going to look through 200 components. The probability that any one of these individual components passes is 0.95 or 95%. And in this case, we want to find the probability that 190 components, and 190 components exactly pass. And in this case, the probability of 190 components passing is 0.128 or 12.8%. So let's go back to the document and write this out. So I'm actually just going to write it out over here. The IB does allow for calculator notation, and in some cases, I think that's actually, in some cases, the most straightforward. So I'm actually just going to write this out here. Binomial PDF, number of trials, probability of occurrence, and then we have number of successes. And we found that probability to be equal to 0.12835. So to 3 sig figs, this is just 0.128. All right, moving on to part E. Find the probability that at least 188 components pass test 2. So in this case, we have a range of values, at least 188 components. So essentially, we want this to be 188 or more. So 188 all the way to 200. In this case, we still have a binomial. We still have set number of trials, probability of success, and then in this case, we have a range of successes. So let's go back to the calculator. In this case, we'll actually run binomial CDF because we have a range of values. So menu, probability, distributions, CDF. 200 total trials, probability of success, 0.95. Lower bound, it's at least 188, so 188 and above, or 188 inclusive, going all the way up to 200 as our upper bound. In this case, there is 0.79648. That is our probability, or I guess as a percentage, we could say 79.6% chance that we have between 188 and 200 successes. So let's go ahead and write this out. I'm going to write it out under here. I'm going to actually use calculator notation again. This is one of the cases where the IB does allow you to write calculator notation. So binomial CDF, 200, that's our set number of trials, probability of occurrence, at least 188, up to the total value of 200. And in this case, the probability is 0.7964 or 0.796. So I guess maybe just to expand just a little, binomial CDF, binomial PDF, PDF is just the exact value. CDF is a range. And once again, calculator notation is condoned here, but don't generalize this further as if, for example, you had like a scientific notation and you had, 1.2 times 10 to the 6. On a calculator, this would be, for example, 1.2 E6. The IB doesn't like that, of course. This is non-standard. So don't generalize this, I guess, more broadly. In case of binomial and normal distribution, you can use binom PDF, binom CDF, norm CDF to talk about distributions, but not more generally in terms of calculator notation. All right, let's go on. Final question of part 2. Here we go. Instead of testing all 200 components, Zakir now decides to test a random sample of 12 components from a box of 200 components. He decides that the box will only be dispatched if at least 10 of the 12 components pass both test 1 and test 2. The results of test 1 and test 2 are independent. Part F asks us to find the probability that the box is dispatched. Okay. So in this case, he's coming up with a kind of new test. And instead of going through all 200 components, he's going to reach in and grab 12 components. And a box is only going to be dispatched if at least 10 of these 12 components pass both test 1 and test 2. And what we want to do is find the probability that the box is dispatched. That is to say, at least 10 of the 12 components pass both test 1 and test 2. So what is it for a box to pass both test 1 and test 2, also knowing that they're independent? So to pass test 1, a component needs to be between 2.3 and 2.7 grams. We found that earlier in C1. Here it is. And we said, okay, well, a component will pass test 1 81.8% of the time. So he reaches in, he grabs one of these components, he subjects it to test 1, and 81.8% of these components go through. But it's not done yet, they haven't successfully passed, because they need to pass both test 1 and test 2, right? So we can say T1 and T2. So 81.8% will pass this original test, but what is it for them to pass test 2? Well, they also need to pass test 2, which occurs 95% of the time. So we reach in, we grab one of these components, subject it to test 1, 81.8% probability of going on to test 2. After that, there's only 95% of these that make it past the first will go on and actually pass the final. So in this case, we have two independent events. We still have a compound event, so there's two things happening. And in this case, we have probability of test 1 and test 2. Since these are independent, it's just going to be probability of T1 times probability of T2. So what is it for a particular component to pass both test 1 and test 2? Well, since they're independent, we can just multiply the probabilities. So in this case, 0.818, that's probability of passing test 1, and 0.95, that's probability of passing test 2. So let's go to the calculator and find the probability that a component passes both of these tests. So here we go. This is 0.818 times 0.95. And the answer is 0.7771. So let's write that out. 0.7771. Okay, I'm going to erase this. I don't think we need it anymore. I'm going to clear up some space here. Okay. So in this case, we know the probability that an individual component is going to pass both test 1 and test 2, and that's roughly 77.7%. So in this case, although it's actually 4 marks, which seems potentially a little high, and we maybe think that it's maybe more involved than it is, we actually have, once again, a binomial distribution. That is to say, we have a set number of trials, 12 trials or 12 components that we're going to select. And we want to find the probability that at least 10 of these 12 components pass both tests. So set number of trials, we have the trials being independent, that is to say, one component passing both test 1 and test 2 doesn't influence the probability of the next component passing or not passing both test 1 and test 2. So set number of trials, we have a constant probability of occurrence. The events themselves are independent of one another. And then, of course, we have a number of successes, or in this case, a range. So here we actually have a binomial distribution once again. So maybe actually I'll write this one out in a little more detail. So here we have a binomial distribution. We have the number of successes. We also have, maybe we'll put this one just lower. We have the number of trials. We have the number of successes. And we also have probability of success. And of course, it's important to know that they're independent of one another as well. So number of trials is 10. Number of successes, number of trials is 12. Number of successes is 10. Let's call the number of successes x. X is greater than or equal to, greater than or equal to 10 and less than or equal to 12. And the probability of success is equal to 0.7771. I'm actually going to use colons just for good form. All right. Okay, so let's go into the calculator and work this out. Here we go. So, menu, probability, distributions, and let's go binomial CDF because we have a range. Here there are 12 components that we'll be assessing. Probability of success 0.7771. Lower bound, it's at least 10, and the upper bound is 12 inclusive. Okay. So, probability that an individual box is dispatched is 0.478779, or as a percentage to 3 sig figs, this would be 47.9%. So that would be the probability that a box is dispatched. That is to say, at least 10 of the 12 components pass both test 1 and test 2. So let's go ahead and write this out. So here we have binomial CDF. We have total number of trials, probability of success. We have number of successes, and then, of course, a lower and upper bound, so between 10 and 12. And the answer in the end is 0.478779, or I guess to 3 sig figs, this would be 479. Okay. Kailash manufactures drink containers in the shape of a cuboid. The container has a square top and a square base of length L centimeters. Its height, d centimeters, is 3 times the length of the base. Part A asks us to write down an expression for d in terms of L. So they tell us here that d is 3 times the length of the base. So what does that mean? That means that d is equal to, well, 3L. So if d itself is equal to 3 times whatever the length of the base is, d is equal to 3L. That's all we would need to write. We can write d is equal to 3L, or we can just write 3L. I'm going to write d is equal to 3L. Okay, the container can hold 375 cubic centimeters of drink. Part B asks us to find the value of L and D. Okay. So right now, looking at this container, we just have D and L, but we don't have any values. But here they tell us the volume. So they don't actually use the word, but they're telling us, and I guess they're giving us cubic centimeters here. They're telling us that the volume is 375 centimeters cubed. So what is the volume in this case of a square-based prism? The volume for any prism is going to be area of base multiplied by height. So in this case, if we find the cross-sectional area, this area of the base, and then multiply it by the height, then we can find the total amount of space it takes up, and another word for that is the volume. So what is the area of the base? Volume is equal to, here we have a square. Area of a square, I think this is actually in our formula booklet, is just L times L, or L squared. And what is the height? The height is equal to D. We actually know a few of these values. So we know the volume is 375. So let's actually substitute that here. 375 and L. But now we have it in terms of L and D. If we can write this just in terms of one variable, because right now it's L squared times D, we can't solve an equation if it's in terms of 2 variables, because there's a whole bunch of combinations of L and D that's going to satisfy this. So what we want to do is we want to create an equation where it's just in terms of L. And how can we do that? Well, here we have a situation where D is equal to 3L. So whenever we see a D, let's replace it with 3L. Remember, an equal sign is essentially an is, right? D is 3L, quite literally is. So in that case, whenever we see a D, we can replace it with 3L. All right. Now we can actually end solve this, but I'm going to clean it up just a little first. This is 375 equals L squared is L times L times another L is going to be L cubed, or I guess we have 3L cubed. You can put this right into end solve and you'll be fine as well. So let's actually go ahead and solve. Let's find the value for L in this case. So here we go. Menu, algebra, numerical solve. 375 equals 3L cubed. And then ask the calculator to solve for L. And we have a value of 5. Okay. So L is equal to 5 centimeters. Let's go back to the document here. L is equal to 5. I think that's kind of refreshing. If it was like the tiniest fraction of a centimeter or some massive amount, I think that would be a little unusual for a juice box, but 5 centimeters seems pretty reasonable. So we know that L is equal to 5. Now what is D equal to? So let's actually write this out. L is equal to 5. Well, here we said that D is equal to 3L, or the height is equal to 3 times whatever L is. So if the height, D, is equal to 3 times whatever L is, then we know it's 3 times 5, or in this case, 15. Okay. In part C, we're asked to calculate the total external surface area of the container. Okay, so surface area of this container is this outer portion. Essentially, if we wanted to wrap it, how much wrapping paper would we need? Or if we wanted to paint it, what is a total area that would be covered? So how can we find the surface area? Looking at this, it's a square-based prism. So we have congruent sides. This base and this height are the exact same, and they're both squares. So if we find this base, then we can multiply by 2 because we know we've got one the exact same right above. Same, since these side lengths are the same, this right here, this wall or this face right here, is going to be the exact same as this wall right here. And since actually they're all the same, it's also going to be the same as the one on the front and the one on the back. So we really just have two shapes that we need to find. We need to find this square, and we know we've got 2 of those. And we need to find this rectangle, and we have 1, 2, 3, 4 of those. So let's find the area of this base first. It's L times L. It's a square. So in this case, L times L is just going to be 5 times 5. So let's just call this, should we? Yeah, I guess we'll call this A1. So A1 is equal to L times L, or L squared. It's this square base. And in this case, it's 5 squared, or 25. And that would be A1. Okay. And what about A2? This rectangular face right here. A2 is equal to, what are its dimensions? It's L times 3L, L times D, essentially. And that's going to be 5 times 15. So L times D, and this is 5 times 15, or this is 75. Okay. Oops, sorry. No, it's not 75. It is 30, 60, yeah, it's 75. Okay. So what did we say right at the beginning? We said that there were 2 faces. This base and this at the top were the exact same. So if we want to find the total surface area, we're going to have 2 A1s, that is to say 2 square faces. And we're also going to have 4 A2s, or 4 rectangular faces. So what was the area of these square bases? 25. And we have 4 rectangular faces, and each of those had an area of 75. So let's work this out. You can go to the calculator and solve this, but I think that is okay as well. 750, our units are centimeters, and these are square units. Okay. Good. Let's go on. Continuing on. To reduce environmental impact, Kailash is trying to minimize the amount of material needed for the production of the 375 centimeter cubed container. He's willing to change the shape to a cylinder with radius r centimeters and height h centimeters, as shown below. The cylindrical container of drink must also hold 375 cubic centimeters. Part D asks us to find an expression for the height h of the container in terms of r. Okay, so in this case, it's not going to be as simple as just saying that h is equal to 3r. In this case, actually, we can't give h a definite value yet. We can only write h in terms of r. That means h on one side, and it's going to be equal to a whole bunch of other stuff, also including the variable r. So how can we link h, r, and this volume of 375 centimeters cubed? Well, we can actually, since they give us the volume, let's ask ourselves, what is the equation for the volume of a cylinder? This is given to us in our formula booklet, and it is equal to pi r squared, or area of the base, times height. This is actually similar to the rectangular prism as well. That is to say, area of the cross-section times extension, or the height. So area of the base is pi r squared, a circle, and then height is still just height. That's also in our formula booklet if we need. Volume is 375. All right. And here we have pi r squared times h. And now what we want to do is we want to write an expression for h in terms of r. So essentially what that means is let's write an equation where h is by itself and everything else is on the other side. So 375 equals pi r squared times h. In this case, we don't want pi r squared times h. We just want h by itself. So how can we get rid of this pi r squared? It's currently being multiplied by h. Let's use inverse operations and divide by pi r squared. Remember, what we do to one side, we have to do to the other. Essentially, this is the idea of balancing scales. You can divide both sides by a half, for example, and the scale still balances. Divide everything by pi r squared. As long as we divide both sides by the same thing, our scale remains balanced. So pi r squared divided by pi r squared cancels out. Anything divided by itself is equal to 1. Now we have h all by itself, and it is equal to 375 over pi r squared. And if we wanted to, I guess we could rearrange this and just switch it to the other side. All right, so there it is. Find an expression for the height h of the container in terms of r. H is equal to 375 over pi r squared. Okay. Let the total external surface area be a centimeters squared. Show that a is equal to 2 pi r squared plus 750 over r. This is a 2-mark question. Okay. So a is the surface area. What is the surface area of a cylinder? Well, we've got this closed surface, and then we've got these two circles, one on the top and one on the bottom. This is pi r squared, so we're going to have 2 pi r squareds. Then what's the area of this curved surface? For this one, we can actually go to our formula booklet, and we can have a look here. So what is the area? So the area, this is kind of nice. Surface area of a closed? No. So they only give us the area of the curved surface of a cylinder, which I think is actually kind of nice in a way. So the curved surface is 2 pi r h. I'm actually going to draw a cylinder right here. So here is our cylinder once again. The curved surface is just going to be this outer portion right here. Whoops. It all went away. There it is. It's just going to be this outer portion right here. But we also have this top and the bottom right here. So this 2 pi r h isn't going to give us the total surface area of the cylinder. It's just going to give us the curved surface. We're still going to need to add on the area of the top and the bottom, which are both pi r squared, respectively. So let's go back and write an equation for total surface area. So area is equal to, well, the two faces at the top. So here's the area of the top, and we have the area of the bottom. Both of these are equal to pi r squared. So we have pi r squared plus pi r squared, or we have 2, I'll use black, 2 pi r squared plus the curved surface, which we found was 2 pi r h, and that was given to us in the formula booklet. Okay, so it looks a little similar to this. 2 pi r squared stays the same, but this 750 over r does not look like 2 pi r h. One thing that we see is this is all in terms of r, where this has an h in it. So how can we get this to look like this, or essentially just looking at this term, how can we get rid of this h? Well, one thing is kind of like a clue is earlier on they asked us to find h in terms of r, and we've set up some equation where h equals or h is 370 over pi r squared. So if we want to get rid of this h, let's just substitute this business right here in for h, because h literally is this. So wherever we see this h, let's replace this with 370 over pi r squared, and we'll get rid of h and replace it with r essentially. So 2 pi r squared plus 2 pi r, and now we have 375 over pi r squared. All right, now here we're dealing with our fractions a little. We need to simplify this. To be honest, actually, this might be okay because the next actual logical step is this. But just to show you how it looks and how it works, here's 2 pi r squared. I'm going to take the long way and just try to unpack this a little. This is essentially 2 pi r times 375 over pi r squared. Right? That's essentially what our brackets are. When there's nothing in between, it's just multiply. 2 pi r by itself, we can write this as 2 pi r over 1 and create a fraction. And now it's a matter of, do we want to do this? Now let's just cancel out the variables or values that we can. So looking at the top, we have an pi and another pi. Pi in the top, pi in the bottom. Pi over pi is equal to 1. They'll cancel out. Here we also have an r, and then here's an r squared. So we can cancel out one of those r's. So cancel out this r, and then we'll cancel out this r right here. And in the end, what we'll have is 2 pi r squared plus 2 times 375 is 750. 750 over r. And that's what we have here. I was going to potentially draw this part out. I'll show you what I was going to do. But I thought it might be a little too long of an explanation. So this is where we kind of left off at. 375 over pi r squared over 1. I was going to say that when we multiply the tops and the bottom. So essentially we could rearrange these terms, and we could put 375 over 1 times 2 pi r over pi r squared, and then that would make it a little easier to see how we can cancel out and then wind up with this 750 over r. For this final term right here, essentially we're canceling out common factors. Okay. All right, let's go on. But I guess maybe last thing I'll say is this step leads us, the next logical step is actually to this. So after we substitute in for h, the next logical step is actually what the form that we're trying to show. Okay, let's move on to f. All right. Part F asks us to find dA dr, or the derivative of a. So here's a right here. Just going to grab this and bring it down so we can work with it. All right. So we want to find the derivative. In our formula booklet, we have a formula that tells us how to work with a derivative. So if we have some basic function of f of x is equal to xn, how can we take the derivative? So essentially, sorry, if I can just write dy dx. Remember, these two forms are equivalent. And so that's this dA is the same, for example, as a prime. Just different ways of writing it. Still the derivative. So here's f prime of x. How can we take the derivative of this? Let's multiply our exponent out in front. We have n times x, and then n we reduce by 1. So whatever that exponent is, we reduce it by 1. Okay, so let's go and look at this right here. We see actually there's a variable in the denominator, so we're going to need to bring that up essentially and write it with a negative exponent. Just to, I guess, show what that would look like. If we have, for example, 1 over x squared, what does that look like if we wanted to write it with a negative exponent? It would be x to the negative 2. Same if we had, let's say, just x cubed, it would be x to the negative 3. Or in general, 1 over x to the n is just x to the negative n. A kind of helpful way to think about it is if you want to move this x cubed up and you no longer want it at the bottom in the denominator, just move it up, but then shift that exponent to negative. All right, so before we can tackle this, we're actually going to have to remove this r from the denominator and write it with a negative exponent. So a is equal to 2 pi r squared plus 750 stays the same. This r is actually r to the 1, so when we bring it up, it's going to be times r to the negative 1. So we could write times r to the negative 1, but we don't need to exactly. All right, now everything's as it should be, and now we can take the derivative. All right, derivative, remember, just deals with our variable. So pi is a constant. It's a number. It's 3.14, so on, so on, so on. So we don't deal with the pi. We just deal with the variable, this r right here. Let's follow that process. Multiply the exponent out in front. 2 times 2 is equal to 4 pi r plus, actually maybe not plus, to be honest. We'll take this exponent, multiply out in front. So 750 times negative 1 is negative 750. R used to be negative 1. Let's take 1 away from it. Now it's negative 2. So there we have dA dr right here. Okay. Part G, hence or otherwise, find the value of r that will minimize a. Okay, so not a bad question. Let me just erase this right here, provide some room. So hence or otherwise is nice because it gives us some flexibility. Hence usually means you are required to use what has come before. In this case, you would be required to use the derivative to find the value that minimizes a. In this case, we have a little bit of freedom. So there's two different ways. If we wanted to use the derivative, we know that our maximum or minimum will be found when the derivative, dA dr, is equal to 0. And just to kind of give an explanation of why that is the case, let's imagine that there's a simple quadratic in some ways. What is the minimum point of a quadratic? Well, it's this vertex right here. But in terms of the derivative, in terms of the slope, well, how can we use the slope to help us find that? Well, let's look at this point right here. Its slope, its instantaneous rate of change is negative. Here it's negative as well. And then on this side, of course, it's positive. And on this side, it's positive again. But there's going to be one point right here where the derivative itself is equal to 0. That's the point where it's done all of the all of the decreasing that it's going to do, and before it started increasing. So this is the point essentially where it's as low as it's ever going to go. That's the point where it stopped increasing or decreasing, where dA dr is equal to 0. So we could use the derivative. We could just set dA dr is equal to 0, and then essentially we would have something like this. So dA dr is equal to 0. Just replace this with 0, and then we could end solve. That would certainly be a way to do it. Another way is, here is our equation, which links area to the radius as well. We could actually just graph this and find the lowest point. That would also work okay. Either one, actually, whichever one you're more comfortable with. This links surface area to radius. Just graph it and find the lowest point. That's a real world kind of example. If you're comfortable with this calculus, this idea that the derivative equaling 0, or the point where we have a rate of increase of 0, is also going to be our minimum, then that's fine as well. I'm actually going to use, to be honest, it might actually be easier to end solve this, but let's actually solve this way, because I think this is potentially more straightforward and intuitive way, at least potentially. Okay, I'm gonna get a new document. Let's get a graph. And here we have 2 pi r. In this case, we need to write x squared because this is our variable. 2 pi x squared plus, and we have 750 over r, or 750 over x. All right, let's zoom fit, and hopefully it's not too bad. Not too bad, kind of, sort of. So I'm gonna move over just a little. So this function, surface area, the radius can't be negative, so we can ignore all this. Radius can be positive. This is surface area. It looks like it goes towards infinity. And then it goes low, 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 low. And then it starts increasing once again. There's going to be some minimum point where the surface area is, well, minimized. So let's go Menu, Analyze Graph. And let's find that minimum point. Here it is. So when r is equal to 3.908, then our surface area is minimized. So let's go back to the document here. We're going to erase some of this. And since this is a 3-mark question, they're going to expect some process. If you solved it graphically, and you can just graph this equation, or this function rather. So here we go. This is a as a function of r, and we've got this rational equation which goes all the way pretty low, and then it starts increasing again. But what was its minimum point? Its minimum point right here was equal to 3.908 and 200, let me give it a little more space, 287.87, or, well, right, 287.9. Okay. And find the value of a, oops, sorry, we're still on this one right here. Find the value of r that will minimize a. R itself is this x coordinate, and that's 3.91 to 3 sig figs. Okay. Find the minimum value of a needed for the cylinder. Okay, we know what r is. Here is a function which links both r to a. We can just plug in a value of r into this function, and we would find the surface area. But actually, going back to our calculator here, this is already a graph which links area to the radius. So we actually already know that when r is equal to 3.908, a, the surface area, is equal to 287.87. So this is already a function which links r to surface area, or r to surface area. So find the value of a needed for the cylinder. Here we are in the document once again. A is equal to 287.9. In terms of the process, we could either substitute into this function right up here, or the graph gives us this information as well. Okay. Last question here. To produce the containers, additional material is required. 10% additional surface area for the cuboid, 25% additional surface area for the cylinder. Kailash will choose the container that requires the least amount of material. Determine which container Kailash should choose. Justify your answer. Okay. So we found some calculations for the cuboid and the cylinder, but in order to make these, they're going to require a little bit of kind of buffer, I suppose, a little bit of cushion in terms of the amount of material that we'll need in total. So which one uses the least amount after this kind of cushion is factored in? So let's find the surface area of the cuboid. We'll increase it by 10%, and we'll do the same for the cylinder, but increase it by 25%. All right. So what was the cuboid again? The surface area, close. The surface area of the cuboid was 350 centimeters squared. So let me write this as SC, surface area of the cuboid. And then, that's not going to work because we have a cylinder. So let's call this S1. And then S2 we'll call the cylinder, which we had equal to 287.9. 287.9. Okay. So what we're going to need to do is multiply this to factor in this 10% additional material that we'll need. So how can we do that? Two different ways. I think the most straightforward way is just to take this 350 and then multiply by 1.10. Why 1.10? Because we have 100%, then we're adding 10%, or essentially we'll have 110% of what we had originally, which as a decimal is 1.10. The other way you can possibly do this is you can say, okay, there's 350. What is 10% of 350? 10% we know is equal to 0.1. And you can say, okay, 350 times 0.1 is 35. And then you can say, okay, I've got 350, and now I'm going to add 10%, which is 35. You can do that as well. In some ways it's more conceptual and maybe even more intuitive, but I think in one step, this way is nice as well. We have 110% of what we had originally. All right, let's actually work that out. Let's work this out. So 350 times 1.1, and it should just be adding that 35 again. So here we are, is 385. And what about for S2? We have 287.9, and in the same way for S2, we'll have what we had originally, plus we'll need 25% extra, or we'll need 125% of what we had originally. As a decimal, that's 1.25. All right, so 287.9 times 1.25. Let's go to the calculator. 287.9 times 1.25. This is equal to 359.875. Let's write that out. 359.875, or to 3 sig figs, this would be 360. So, which container Kyla should choose? He should choose the cylinder. So, let's say area cylinder is less than area of the cuboid. That is to say, 360 centimeters squared is less than 385 centimeters squared. Therefore, he should choose the cylinder. All right, there we go. Question 4. On a particular day, the height of the tide, h, in meters at Albion Harbor can be modeled by the function h of t equals negative 2.5 cos bt plus 4.5, where b is an element of the real numbers and t is greater than or equal to 0 and less than or equal to 24. b being an element of the real numbers means that it can be positive, negative in this case, or it could be a decimal fraction. It doesn't necessarily need to be a whole number. And t represents the number of hours after midnight. Okay. The graph of h is shown in the following diagram. So here we have the height in this harbor against time, which is measured in hours. All right. Show that the value of b is 30. So one more question. So b is right here. So within our standard form, and this is a cosine function, but we can represent it as a sine function or a cosine function. Let's say we have something like this, f of x equals a, I'm going to use sine just because it's a little more common, bx plus d. A, remember, is our amplitude. B is our frequency, the number of up-down cycles within, I guess, 360 units. But b is our frequency, and d is the principal axis, what we shift this function up or down by. So in this case, they're asking about b. B is the frequency, and b is given by 360 over the period. And the period, once again, is number of cycles, or sorry, not the number of cycles, but the time taken to complete one cycle. So one up-down cycle, how long does that take? So if we can find the period, then we should be able to find b. So let's see. In this case, we can usually go from peak to peak, or what's called trough to trough. And I think this trough to trough will actually be pretty good. So here we go. It has its first minimum right here, which would be, I guess, negative cos. So it has its first minimum here, and then its second minimum right here when x is equal to 12, or sorry, when t is equal to 12, I guess, in this case. So the total time that has elapsed is 12 hours, time taken to go from trough to another trough is 12. So looking at this value of b is equal to 360 over period is 12, and this will give us a value of 30. All right, and I hope that was, yeah, there it is. So show that the value of b is 30. There we go. So for this, they already have the answer. Process would be 360 over the period. Time taken for one complete cycle is 12, and that in the end will equal 30. All right. Let's go on to question B. Find the height of the tide when t is equal to 5. All right. So insofar as we found b, we actually have the complete function here. So now we have a function which relates the height to time. And so we can just plug in the value of 5 into our completed function, and then we should be able to find the corresponding height. So let's go ahead and do that. So I'm actually going to erase some of this here and just clear up some space, and I'll use this space right here. Okay. So our function right here is h of t equals negative 2.5 cos, and we found out, or we confirmed, I suppose, that b was equal to 30 plus 4.5. And down here they're asking us to find the height when t is equal to 5. So let's substitute 5 in for t, wherever we see it. So negative 2.5 cos 30, and times 5, I guess, plus 4.5. All right, let's put this into a calculator, and we'll solve for h. Here we go. So we have negative 2.5 multiplied by cos 30 times 5 plus 4.5. Make sure you're in degrees. And here we go. So the height when time is equal to 5, or the height at 5 hours, is 6.66506. So let's go back to the document and work this out. Find the height of the tide when t is equal to 5. So, sorry, I think I might have said time back there, but really the height is 6.665. So height is equal to 6.665 meters, or to three significant figures, this would be 6.67. And there's the answer right up here again as well. Okay. Moving on. Part C asks us to write down the amplitude of h and the equation of the principal axis. So maybe I shouldn't actually have erased what we had here, this kind of general form, but I'll bring it back actually. So actually, what I'm going to do is I'm going to take our completed function right here and then compare it to what we have. No, I'm going to do it up here. And compare it to this general form. So normally we would have some function f of x is equal to, and then we would have a cos bx plus d. And here they're asking us to find the amplitude and the principal axis. So the amplitude is just the coefficient, what we multiply, let's say, our function, either cos or sine by. And the amplitude is itself a magnitude. What the amplitude is, I suppose, in the context of our trig function, is the height of the wave itself. So if this is our principal axis, or the midline, what is the amplitude? The amplitude is essentially the height of the wave, or the distance from the maximum to the midline. This would be our amplitude. Or let's say this would be our amplitude, essentially the height of the wave. So amplitude, we just want the magnitude in terms of the height. We don't want to include the negative. So in this case, what is the amplitude? The amplitude is 2.5. This is essentially the height of our wave. So let's go down here. The amplitude of this function is equal to 2.5. So once again, we just want the magnitude, the absolute value. No negatives. We just want to know essentially how high is this wave? What is the distance of this wave from the principal axis? What is the highest point in terms of its distance away from the principal axis or the midline? All right, and what is the equation of the principal axis? So let's look at this once again. So the principal axis, I've called it a midline a few times. This is essentially the value d right here, what we shift our function up or down by. Usually, or just kind of by default, I suppose you could say, our sine function, something like this. Max is 1, min is -1, starts at the origin of 0, 0. But that's not going to suit all of our real-world situations. Sometimes we're going to want to shift this function up or down. And that's what this value of d does. So essentially here in this case, we are shifting this is a cosine function, but we're shifting it up 4.5 units. So in this case, the location of the principal axis, which is usually just around y is equal to 0, is now at 4.5. So what is the principal axis? It is 4.5. In this case, they're asking for an equation. So let's set up an equals here. The equation of the principal axis is h is equal to 4.5. I don't know, I'm wondering if the mark scheme, if we were to write y is equal to 4.5, that would be accepted. I'm not sure, just because our variable in this case is h, the height. I'm actually going to check out the mark scheme here. So h of t is equal to 4.5. Word A1 for an equation of a horizontal h equals constant. So they would accept y equals a constant. Okay. All right, let's keep going. I guess the last thing I'll say about this in terms of the principal axis, more familiar in terms of this value of d right here. You might have seen this as in max plus min over 2. That is to say the halfway point between the highest and lowest value. So if you wanted to, you could potentially sketch this function, find its highest point, its lowest point, and then take the average, and that would be your midline as well. But I guess just recognizing A, amplitude, D, principal axis, that might be a nice kind of quick way to work it out as well. All right, moving on. Boats can only leave or return to Albion Harbor when h of t is greater than or equal to 2.65. Robin wants to leave the harbor to go fishing as soon as possible after the time is 12. Determine the earliest possible time that Robin could leave the harbor. Give your answer to the nearest minute. Okay. So to leave the harbor, the height of the water needs to be greater than or equal to 2.65 meters. This function right here starts where t represents the number of hours after midnight. Number of hours after midnight would be 0000. And Robin wants to leave, in this case, after 12 or 12 noon, I guess we could say. So in this case, the height itself, let me erase some of this. The height needs to be above 6.25. Actually, I'm going to keep this blue and just kind of repurpose it. So it needs to be above 2.65. And I'm not sure where exactly that might be, but we can imagine, for example, that maybe it's right here. And so if this is h equals 2.65, then if this is 12 noon when he wants to head out, he would, let's say, go to approach the harbor, and the harbor master would say, I'm sorry, the water is not high enough yet, it's too dangerous. And he would have to wait. And the question is, when is the earliest time in which he can leave? Well, in that case, he's going to have to wait to, this point. And our goal is going to be to find the intersection. That is to say, what is the time in which the harbor, or the water level in the harbor, is now above this line of 2.65. So for this, we can do a few things. We can use nsolve creatively, or we can graph this function. I'll show you both. Okay, so to do this in either case, we're going to need this function right here. So let's go into the calculator and work this out. We'll go into our graphing calculator first. We can't solve this with nsolve, but I think graphing might give us a better visual picture here. So let's put in the function itself. And the function was equal to negative 2.5 cos 30, we would write 30t, but this is in terms of x. So we'll write 30x plus 4.5. And so here's our function. It's actually not too bad. I don't think we need to adjust the window. Let's just drag this over. And this is pretty good. So it has, for example, one complete cycle. And if we want to use graph trace, for example, put in a value of 12. So this, for example, is when Robin would like to leave. And it looks like it will show that intersection point that we might be looking for. So here it is. It's a function which relates height of the harbor to time. Let's put in that value for height. So let's get graph entry function, and let's create this line of 2.65 meters. Okay. So here we have function height against time. This, once again, was the point where Robin would like to leave. If I can just get graph trace, there we go. That's when he would like to leave, but he can't leave yet. He's got to wait until the height of the water is above this point. So let's find this intersection point. So intersection right here. So it's not until 13.409, or roughly 13.4 hours have elapsed after midnight. So let's go back to the document and write this out. So here we go. Just to show process a little more, let's write out this h of t is greater than 2.65. So h of t was itself equal to negative 2.5 cos 30t plus 4.5. And we wanted to find out when h of t was greater than 2.65. Greater than or equal to 2.65. All right. And we did that. We found out that point was when t was equal to 13.409. So once again, this point right here, this is when t is equal to 13.409. That's exactly the point at which height is equal to 2.65 meters, and then after this point, it's now safe to leave the harbor. So here there's actually one other part of this 3-mark question. They're asking us to write this out to the nearest minute. So what do we have here? We have 13 whole hours plus 0.409 hours. So I'm actually going to write this out and split it up in this kind of way. So here we have 13 hours plus we also have this 0.409 hours. So 13 hours can stay, but we don't really talk about hours. We can talk about like a half hour, a quarter hour. But in this case, even if we wanted to say, hey, it's, you still have to wait 0.409 hours. Here they're asking us to write it in terms of minutes. So give our answer to the nearest minute. What is 0.409 hours in minutes? Well, we know 1 hour. We know 1 hour is itself equivalent to 60 minutes. In this case, we don't have a complete hour. We've just got a fractional amount of an hour. We've got roughly 41% of an hour. So what is that? Well, let's take 60 minutes and multiply it by 0.409. And that will tell us the fraction of an hour that we have, but in minutes. So let's go back to the calculator. Here we are, 60 times 0.409. And this gives us 24.54, or rounding to the nearest minute, this would be 25 minutes. So going back to the document here, this is 24.54, or 25 minutes. So what do we have? We have 13 hours plus 25 minutes. And if we wanted to express that as a time that, let's say, someone could read on their watch, or if you wanted to meet someone at that time, for example, that would be 13:25. All right. So the earliest possible time that Robin can leave the harbor to the nearest minute is 13 hours and 25 minutes after midnight. Okay. The boat will take 15 minutes to travel from the harbor to the fishing site. Robin intends to return to the harbor on the same day. Part E. Determine the maximum length of time he could spend at the fishing site in hours and still be certain he will be able to enter the harbor on his return. Okay. So the earliest time he can actually leave, right after 12, would be at 13:25. So on this 24-hour kind of time scale, I suppose. So at 13:25, he can leave. It's going to take him 15 minutes to get to the fishing site and 15 minutes to get back. And essentially, well, what is the latest time he can come back before the harbor closes? So remember, the harbor closes when it's 2.65 meters or less. So here it is again, 13.409. Here he can go, he can fish, he can fish, he can fish. And then here, if he arrives at this point, anything beyond this point, he's too late. So if this is T1, the exit time, what is T2? That's going to be important in terms of the final time that he can actually arrive at this harbor and still make it in. And then, of course, we're not actually just interested in this. We want to know the total amount of time that he can fish. So it takes him 15 minutes to get there, 15 minutes to get back. So this will be the total time that he's out of the harbor. T2 minus T1. T2 minus T1. Here he's out of the harbor. But he's not just like fishing right outside of the harbor. He needs to travel 15 minutes to the site, and then he needs to travel 15 minutes back. So in terms of, let's just write, what can we write? Let's call it, maybe this is a little, I'd almost say like abusive with our variables and so, but let's call this fishing time, FT. Fishing time is equal to T2 minus T1, but that's not his total fishing time. It's not just the time that he's out of the harbor. He's also losing 15 minutes of travel time there, 15 minutes of travel time back. So he's losing 30 minutes. He's losing 30 minutes of travel time. So it's not actually just 30 though, because T is itself represented in hours. So total time that he's out of the harbor, this is going to give us a value in terms of hours. And so how can we write this 30 minutes in terms of an hour? Well, that is equal to 1/2 hour, or if we want, 0.5 hours. So minus 0.5. And if we can solve that, then we can find the total amount of time that he is able to fish. Okay, so we know T1. Let's go back to our graphing calculator and find T2. Okay, here we are. I'm actually just going to pinch zoom this, or pinch move it, I suppose. Here we go, 13.409. He's out, he's fishing. Analyze graph, intersection, and there he is. He's able to not fish until this point, but he's got to make sure he's back by 22 hours, 0.591. So let's actually go back to the document and write this out. So here we are. I think we're just going to have enough space here. Fishing time is equal to T2 minus T1. So what is this total time that elapses? It's the difference between T2 and T1. T2 we found to be 22.591. 22.591. So 22.591 minus T1, which was 13.409. That gives us this time right here, but he's not yet fishing all that time. He needs to go there and back, and he's going to lose a 1/2 hour of his fishing. So minus 0.5. Let's work this out on the calculator, and then we'll find his total fishing time. So here we are again. I'm going to go back to this. No, that's not useful. Okay, T2 minus T1 minus the 1/2 hour that he loses traveling. Okay, so overall he can fish for 8.682 hours. So let's go back to the document. 8.682 hours. And let's see if they need us to write this out in minutes. Determine the maximum time, the maximum length of time he could spend at the fishing site in hours and still be certain he'll be able to enter the harbor on his return. So in this case, we don't need to convert it to minutes. He can spend 8.682 hours fishing and still ensure that he makes it back on time. Okay. Question 5. The diagram shows the cross-section of a bridge and a river. A coordinate system has been added with the origin O at the point where the bridge meets the water on one side. All units are in meters. A researcher wants to calculate the volume of water that flows under the bridge. To do this, he takes measurements of the depth every 1.9 meters from O. The depths are shown in the following table. So here we have the researcher taking an initial measurement when he is 0 meters, or right at the riverbank, and the depth is 0. 1.9 meters in, the depth is 1.68. Another 1.9 meters, or 3.8 meters in, the depth is 2.81, and so on. What they're asking us to do in part A is use the trapezoid rule to find the cross-sectional area of the river as it passes under the bridge. Okay. So we want to find essentially this right here, this cross-sectional area of the river. Okay. So let's go and look what our trapezoid rule looks like, or see what our trapezoid rule looks like. And I know sometimes it can seem intimidating, but I don't think it's potentially as bad as it really looks. One thing that I think can be simplified in general is this h. I know they give us this formula or this way of calculating h, but h itself is just the width of any individual trapezoid. So for example, if the trapezoid is like this is h. What is the width of an individual trapezoid? So usually it's h. We call it h just because our trapezoid formula, the area of a trapezoid, is what can we say? A plus b over 2 times h. So why do we call this width h? Because we've rotated our trapezoid when we use the trapezoid rule. So all h is the width of an individual trapezoid. In this case, we know the width is 1.9. So most of the time, actually, this formula we can always rely on. We can always use it if we need. Essentially, it's the total distance that we travel. Total distance that we travel, b minus a, divided by number of trapezoids. So for example, if you go from here to here, and you divide it up, let's say this is 10, and you divide it up into 10 trapezoids, 5 trapezoids. Let me erase this. This b minus a over 5, this is just an example. Let's say you travel from 0 to 10, 10 minus 0. Distance that you travel, there are 5 trapezoids. Each of them has a width of 2. That's all h is. H is just the width of an individual trapezoid in our trapezoid rule. So we can always use this formula, but sometimes we can just read it from the question. After that, it's y naught plus yn. This just refers to the height or the depth at a given point. In this case, it's the initial point and the last point. And then after that, we want to take 2 times the sum of all of those intermediate heights or depths. And we'll see what this looks like in practice as we work through this. There's some other videos that kind of unpack this and explain why we only take the initial and the final heights, but why we multiply all of the intermediate heights by 2. I think those are helpful conceptually, but it's been covered a few times, so I want to actually just get to applying the trapezoid rule here. So let's actually write it out here if we can. I think there's enough space right here, at least for the beginning, because I want to get all of this here. Okay, so what is the trapezoid rule? It's 1/2 h y naught, actually I'm going to need a double bracket, y naught plus yn plus 2 times all of our intermediaries. That means 1, y1, y2 plus all the way up to everything 1 less than, well, whatever n is, so n minus 1, yn minus 1, right up to the one before the last. Okay, let's go ahead and substitute 1/2 h. So what is h? We can do this. We can go 7.6 minus 0, end point minus beginning point, divided by total number of trapezoids, 1, 2, 1, 2, 3, 4. We could do that, and we'd find out that that gives us 1.9. I think the easier way, just remember h is actually the width. The width of the trapezoid, which is 1.9. They tell us that the researcher goes and measures the depth every 1.9 meters. So h itself is 1.9. Now let's open up, be careful with the double brackets. That's sometimes an area that can be confusing or an area to potentially trip up on. Y naught plus yn. So y refers to, in this case, the depth. The height, or in this case, the depth, when we're right at the riverbank is 0. So y naught is equal to 0. And yn, the final point, when we are 7.6 meters away, that final height is equal to 0 as well. Plus 2 times all of the intermediate heights. That means 2 times this, times this, times this. And just kind of maybe too quickly, why do we multiply 2? Because when we're looking at these trapezoids, here's one trapezoid, here's another trapezoid, and so these intermediate points are essentially the walls that are shared by 2 trapezoids. So the beginning point and the end point, they're not shared by any other trapezoids except for their own. But these boundary lines, or the walls, I suppose you can say, of these trapezoids are shared between 1, 2 trapezoids. That's why we multiply all of these intermediate values by 2. So 2 times 1.68 plus 2.81 plus 2.32, close the brackets. All right, and this should give us an estimate for the total cross-sectional area of this river. So let's go to the calculator here, and let's write this out. So 1/2, you can write it as 0.5, but that's fine, multiplied by 1.9. Whatever this value is, we want to multiply it by everything within this larger parentheses, brackets right here. We don't really need to write this, but I'm going to write exactly what we have just for consistency. So 0 plus 0 plus 2 times, this was all of those middle values, 2.81 plus 2.32. All right, half times 1.900, 2 times 81, 2.32. This looks good. All right, so cross-sectional area, our estimate is 12.939 to 3 sig figs. This is 12.9. Okay, so let's go back to the document here. Here we are. And our estimate, our approximation essentially of this cross-sectional area is 12.939, or what could we say, 12.9. And then what are our units? I suppose they are meters squared. Okay. Let's keep going. The water flows under the bridge at a rate of 0.3 meters per second. Find the volume of water that passes under the bridge each second. Kind of a neat question. I think it is. So what can we do? I think actually we can even kind of relate this to our prism question earlier when we found out the volume of these prisms. For each of these cases, for this cylinder and then also for our square-based prism above, we found the volume by taking this cross-sectional area and then multiplying it by the height. So in this case, I'm actually going to go back. If we want to find the total volume of water that passes through some point, what can we do? What can we do? I'm going to try to represent this as best I can, I suppose. So here, let's imagine this is the riverbank, and then this is the area under the river. And then the river flows along. Here's the river flowing along, I suppose. I can do a better job with that. All right. And we imagine that, for example, what can we say? What can we say? So what is another way to represent this 0.3 meters per second? How can we make use of this? So one thing that we can do, again drawing on this idea of cross-sectional area and then volume, another way to think about this, and it's kind of abstract and it kind of shifts perspective in a certain way, is if the river flows at 0.3 meters per second, we can imagine that 0.3 meters of river flow through a given point. So of course a river itself isn't just stationary. The water, of course, is made up of atoms, and they move around, and there's all this kind of like fluid dynamics going on. And so, but if we imagine that this right here is 0.3 meters of river, then what can we say? If we imagine that this is, let's say, uniform cross-section, we can say that 0.3 meters of river flows through or flows past a given point, in this case this bridge, every second. So once again, it's kind of an abstract way to represent this, but here's some cross-sectional area. And let's say we're sitting by here, and let's even imagine that we've painted this river, this section at least, if we could, hypothetically. Let's imagine we painted it green. And here we are sitting by the edge of the river, and in some abstract kind of world, there is this 0.3 meter long section of river that is painted green, right? And earlier we calculated the cross section of it. Sitting by this edge of the river where we witness this blob, this green blob that has extension of 0.3 meters, how long does it take for this blob to pass us by? Well, it takes exactly 1 second for it to pass us by. So what is the total volume? What is the total volume of water that has passed us by? Well, we can imagine this chunk of 0.3 times this cross-sectional area right here. That would give us the volume. And I hope that is one way in which we can understand this. So water flows under the bridge at a rate of 0.3 meters per second. So every second, 0.3 meters of water times our cross-sectional area has flowed by us. All right. So what is this shape? It's a rather awkward shape, but we found an approximation for its cross-sectional area, 12.9 meters squared. So we imagine that this is a prism, and we know, for example, area of the base times height. Volume itself is equal to, we often call this area of base, but really it's cross-sectional area. And then often we say area of base times height, but really it's extension. So this we can also write as cross-sectional area times extension. In this case, we know that this cross-sectional area is 12.9 meters squared, and we know its extension is 0.3 meters. So 12.9 times 0.3. This is the amount of water that flows past this given point at any given time. All right, let's go to the calculator and work that out. So here we go, 12.9 times 0.3. And this is going to give us 3.87, and then our units would be cubic, so cubic meters. So 3.87 cubic meters of water flows past this given point every second. All right. Abstract question, I think it's kind of cool. I'm still trying to think if there are other ways that we could represent this, another way to possibly conceptualize what's going on. But the best way that I can think of it, at least right now, is here's our cross-sectional area, and if we imagine that there's some extension to it, that every single second 0.3 meters of river kind of flows by, then what is the total volume of water? Well, cross-sectional area times extension. Basic way we write this is area of base times height. And that's our volume of river, or the volume of water rather, that passes by every second. Okay, let's go on. This one looks a little too familiar. I think that is an error. Time to hang it up. Time to hang it up. Exam's over. A boat is traveling along the river. The cross-section of the boat and the water level is shown in the following diagram. The top of the boat is parallel to the water level and has a width of 5 meters. The height of the boat is 2.35 meters above the water level, and the lowest point of the boat is 1.6 meters below the water level. Here's our boat. There's the water level. The boat is traveling down the center of the river. Part C. Find the vertical distance between the lowest part of the boat and the bottom of the river as it passes under the bridge. So we're told that the boat is traveling down the center. So let's go look at that. So the center would be right at 3.8 right here. So what is the depth at 3.8? The depth of water is 2.81 meters. So the total depth of water is 2.81, but we want to find the vertical distance between the lowest part of the boat and the bottom of the river. So 2.81 meters, that's the bottom, and this boat goes down 1.6 meters. So maybe I'll write it here actually. So here we have 1.6 meters. This total distance right here we know is equal to 2.81. So essentially our calculation is this distance right here. Maybe I'll use a different color. Use red, I suppose. This distance would be equal to 2.81 minus 1.6, which would actually just give us 1.21 meters. So a fair bit of clearing between the bottom of this boat and I guess the bottom of the river. So find the total vertical distance between the lowest part of the boat, 1.6 meters, and 2.81. Was it 2.81? Yes. Okay. 2.81 minus 1.6 is 1.21 meters. 1 mark question, no need for process. We can actually just put 1.21. All right. The curved arch of the bridge can be modeled by the equation y equals negative 0.15x squared plus 1.14x plus 0.9, where x is greater than or equal to 0 and less than or equal to 7.6. Part D asks us to find the maximum height of the curved arch above water level. Okay, so let's go back to our arch right here. Here it is. We imagine it's symmetrical over this distance from 0 to 7.6. And in that case, if it really is symmetrical, and we'll graph it to find the highest point above this water level right here. But if it really is symmetrical, then our highest point will occur right at the vertex. That is to say, right where we essentially split, this quadratic. So we would expect it to be right here, if that is indeed the center or the midline of this quadratic. So the axis of symmetry rather, not midline. So let's go and graph this function, and then we can find the maximum height above the water level. So let's go to our graphing calculator right here, and we'll write out this function. 0.15x squared plus 1.14x plus 0.9. That looks good. All right, nice that we don't need to adjust the window or anything. Analyze graph, let's find the maximum. And here we go. The maximum occurs, right at the center of 3.8, and the height of this arch is 3.066, or 3.07 to 366. So let's go ahead and write this out. So D, I'm going to actually sketch this because It's a 2-mark question, and just to be mindful of process. Oops, can do a little better. There we go. Vertex occurs at this point of the vertex, 3.8 and 3.066. So what is the maximum height? H is equal to 3.07 meters, and that's to 3 sig figs. Part E. Determine whether the top of the boat will be able to pass under the bridge. Okay, so we've got this arch right here, or this quadratic that maps this arch, and we want to see whether this boat, which is actually quite large in terms of its width, will be able to pass underneath. So the boat is traveling down the center, and so what does that mean? If this boat, for example, is 5 meters in width, and it's passing down the center, how far is it going to, in some sense, hang over on either side? So let's actually, I want to use this graph right here. I think this will be suitable. So I'm going to just zoom this in a little, and I think we can use this. Okay. So here we go. This boat is traveling right down the center. It's nice that we found the highest point because it tells us our vertex. Our vertex occurs at 3.8. And here's this boat. It's passing down right to the center. And I'm actually going to even show it underwater. It goes down to 1.6. And then what? 2.5 above the water. Okay. So something like this. Let's see. Once again. Okay. So something like this. Something like this. And then up, up, and here's a representation, in some sense, of this boat. Okay, and we know the width of this boat is equal to 5 meters. So if this is the axis of symmetry right here, we know that the boat hangs over on each side, well, by 2.5 meters on each side. So let me get a different color here. This would be equal to 2.5, and this would be equal to 2.5. And what is the height? I guess what we could ask ourselves in this sense is, what is the height of this arch? 2.5 meters to the left and 2.5 meters to the right. Is it going to be greater or less than 2.35 meters in height? So once again, here's our boat. It's traveling down the river. Maybe I can even make it a little bigger to try to capture what's going on in some sense. Here's the boat, and we don't actually know whether it's going to hit the sides of this arch. We don't know if it's going to be, but we know if it's traveling down the center and it has a total width of 5 meters, we know that it's going to, in some sense, hang over, let's say, 2.5 meters to the right and 2.5 meters to the left. So if this is 3.8, we can ask ourselves the question of, well, what is the height of the river at this point right here? That is to say, 2.5 meters to the left of 3.8. 3.8 minus 2.5 is when x equals 1.3. And we only actually really need to solve for 1, but if we wanted to generalize, we could ask the same question and say, what is the height of this bridge when x equals, now we have 3.8, which is this midline, plus 2.5. So this would be 5, that would be 6.3. So we only need to find one of these. And the question is, when we find the height of the bridge at these given points, will they be greater or less than the height of this boat, which is given as 2.35. So we know the boat is equal to, running out of colors here, the boat's height itself is equal to 2.65. So let's find this height when x is equal to 1.3 or when x is equal to 6.3, and is it greater or less than 2.65? Okay, so here we are. Here's our function once again. And let's put in some values for x. So let's put in a value of 1.3. And we see that when x is equal to 1.3, the height of this arch is actually 2.13. And similarly, it's going to be the exact same height if we were to choose this other side where the boat intersects. So when x is equal to 6.3, again, we have this value, 2.12. So going back to the document, here's our kind of representation of this arch. When x is equal to 1.3, the height, the corresponding height at this point, is equal to, let me see if I can clear this up. Let's do this. Height is only equal to 2.13. So in the end, this arch actually has a lower height than this boat itself. So the boat will actually not pass through. So what we can say is, no, arch is not tall enough. Or we could say that the boat will not pass through. Whether the top of the boat will be able to pass through. No, arch is not tall enough. We could say that 2.65 is greater than 2.13. Or we could say, let's say, height of the boat is greater than the height of the arch, essentially. And with that, we would be able to say that no, this boat is, once again, not going to be able to pass through. All right. So that's about it for this exam. I hope it was helpful, and as always, best of luck.